Welcome to Dr. Boxy Teaches Electromagnetism. In the previous lesson, we started a discussion on integral calculus and we looked specifically at the line integral of fields. In this lesson, we will look at surface and volume integral of fields. So let us get started. In order to define surface integrals, we first want to have a way to represent areas of surfaces using vectors. And this is done in the following way. Here is some surface, some sheet. And we define a unit vector known as the normal vector, and it will be represented by n hat. So here is the vector n hat, and it points perpendicular to the surface. And if we represent the area of the surface by the letter A, we then define the vector A as the number A, which is the area of the surface, multiplied by the normal vector. So the vector A is a vector that points in a direction perpendicular to that surface and whose magnitude is the actual area of the surface. So it looks something like this, and it also is perpendicular to that surface. Now, notice that we made a choice here because I said that we define n hat to be perpendicular to the surface, but there are actually two possibilities. You could have chosen it upward or downward. I chose it this time upward, but there is no general convention about how to choose it. And that means that whenever we are working with n hat or A, we need to explicitly mention in which of the two directions we actually chose it. But there is, however, a convention when we're dealing with closed surfaces. So imagine, for instance, a sphere. So here is a sphere. For closed surfaces, the convention is that we always take the normal vector, n hat, to point outward. So for instance, at the equator at this point here, n hat would point in this direction. At the North Pole, it would point upward. And at this point here, it would point in this direction. So when dealing with closed surfaces, the normal vector always points outward. Now, what do we do with this normal vector? What do we do with this representation of areas of surfaces? Well, we want to use it to define something known as the flux of a vector field. So to do that, let's consider again the surface. And we take some vector field, V. And I'm going to draw a couple of those vectors. So one of them can, for instance, be this one. This may be another one of them. This is still another one. And so what we're looking at are different vectors of that vector field V. Now, the flux is defined intuitively as a quantity that represents the amount of vector field passing through that surface. Now, to calculate the flux, we don't actually need the whole vector field V. For each of those vectors, we can divide it into a component which points perpendicular to the surface that actually goes through it, and a component that is parallel to the surface, and that one just moves along the surface. It doesn't actually go through it. So if we want the flux, we don't need the whole vector V for each of those vectors, but only the component perpendicular to the surface. And as we saw in one of the previous lessons, one way to determine the component of a vector in a certain direction is to take the dot product of that vector with a unit vector in the direction we are interested in. So if we look at this point and we want at that point to calculate the component of V perpendicular to the surface, we need to draw the normal vector at that point. So here is n hat. It is perpendicular to the surface. And if we then consider the quantity V dot n hat, that is the component of V in the direction perpendicular to the surface. But that is not all for the flux, because the flux is a measure of how much vector field passes through the surface. But if we take the same vector field but a larger surface, a larger sheet of surface, there will be more vector field passing through it. So it also depends, it's proportional also to the area itself. And so we define this quantity here as the flux, and notice that A times n hat is the vector A. And so this is the same as the dot product of V dot A. And this is what is known as the flux, and we will use it both in the definition of the surface integral and later in many, many applications. So let's go to the surface integral. We consider again the vector field V, which is a function of x, y, and z. And we look at some surface in space here. So something which looks like this. Now, this surface, just like we did with the interval when defining the Riemann integral or the line integral, we subdivided it into smaller parts. Well, we will do the same thing here with that surface. I call the surface S, and I will divide it into n small parts. Something like this. And now we will look at the ith part of it. Let's say that this one here is the ith part of that division. And in this ith part, just like we did in the previous definitions of integrals, we choose a point ci. So this here is, for instance, the point ci. And let us now zoom in on this ith part. So I will make it bigger. It looks something like this. And here is the point Ci. Now, the idea is, what we're trying to do is to calculate the flux through the whole surface S. What we're going to do is to calculate the flux through each of those small parts and then add them up. So we will get a sum of the fluxes through each of those parts separately. Now, if the partition, if the n that we're considering is large enough, each of those pieces can be thought of as small enough such that within that piece it can be considered to be flat, and the value of the vector field V can be considered to be more or less constant. And in that case, we can represent the flux through that ith part in the following way. Imagine that the vector field V at that point Ci looks something like this. So this is V at the point Ci. And we said to represent the flux through this I part, what we need to do is to take the dot product of this vector V with the vector representing the area of this small part. So let's call the area of this ith part delta AI. It is represented by this vector, the delta AI, which points perpendicular to the surface. And so the flux through this ith part is the dot product of V of Ci with delta AI. And if we now want the flux through the whole surface, we need to add all of these. So we get the sum for I going from 1 to n of this flux through the ith part. So this represents an approximation for the total flux through the whole surface of the vector field. Now, as we increase n, we will get a better and better approximation, and in the limit of n going to infinity, we get something defined as the surface integral, which will be written in the following way: the integral, an s below it representing the surface of v dot dA, where you should think of dA as an infinitesimally small version of delta AI. It's a small piece of, it's a vector representing a small piece of surface, the area of a small piece of surface. Just like with the previous integrals, there are mathematical nuances about when this limit exists, when it not only exists but is independent of the CIs, etc. And just like before, the actual discussion on all of those nuances is left to a course in mathematics, but we will use it and we will see how to calculate it on the next couple of slides. Now I just want to add also the same kind of remark that I had with line integrals. Just like with line integrals, if we're dealing with closed surfaces, so for instance a sphere, a cylinder, or any other closed surface, we emphasize the fact that it's closed by drawing a circle on the integral sign. So in that case, the closed surface integral will be written in this way, and it doesn't change anything about the way it is calculated. It's just there to emphasize the fact that it's a closed surface, and as we will see later in this course, it is used all over the place in electromagnetism. So let us see as an example of how to calculate this. We consider the following vector field, and we want to calculate its flux through this surface. Now this is a cube except that it is open at the bottom. There is no bottom. So we're actually only calculating flux through the 5 faces of the cube that are there, which are the front and the back, the left and the right hand side, and the top. Now because it is not a closed surface, the bottom isn't there, we need to actually mention in which direction we choose the normal vector to point, and we choose this time to take the normal vector outward on each of the 5 faces that we are considering. So the 5 arrows that I drew here. The total surface integral we are going to calculate will be the sum of the surface integral on each of the 5 faces. So it will be the surface integral over the first face plus the second face, etc., up to the surface integral on the 5th face. And we will calculate them one by one. For the first face, which is the front one, the one facing us, dA there points, we said the dA points perpendicular to the surface, and because it is outward, it is in the positive x direction, which means that it's a vector that points along x hat, and its magnitude is the size of a tiny portion of the yz plane, or a plane parallel to the yz, and so it is of the form dy dz. So dA is dy dz times x hat, and if we want to calculate v dot dA, what we do normally is multiply their x components plus multiplying their y components plus multiplying their z components, but dA doesn't have a y or a z component. So we're left with the x component of v, which is 2xz, times the x component of dA, which is dy dz. And notice that on the front of the cube, the value of x is a constant value of 2, so we can just plug in 2 for x and we find 4z dy dz. And now we want to integrate this. So it's the integral over face v dot dA, which is the double integral over y and z, where y goes from 0 to 2, z goes from 0 to 2 of 4z. The 4 can be just pulled out of both integrals, so we just get a 4 at the front. And if we now solve the z integral first, the integral of z, so the y integral just remains there. And the integral of z dz is z squared over 2. But it needs to be evaluated between 0 and 2. Now z squared over 2 evaluated in 2 is 2 squared over 2, which is just 2, minus z squared over 2 evaluated at 0, which is 0. So net we are left with a 2, which means we have 8 outside. We already had a 4 and there's an additional 2 coming out now. And we're left with the integral of 0 to 2 of dy, which is just y evaluated between 0 and 2, which gives us 60. So this is the flux through the front of the cube. For the second surface, dA is in this case again dy dz, but pointing in the negative x direction, so it's multiplied by minus x hat. And so v dot dA is minus 2 xz dy dz. But in this case, the value of x on the back face of the cube is 0. So we can just plug in 0 for x and we find v dot dA is 0, meaning that the surface integral over the second phase of the cube is just 0. For face number 3, dA, it's the right-hand face of the cube. So the dA points in the positive y direction, so it will be something multiplied with y hat. And it is part of the xz plane, or it is parallel to the xz plane, so it's of the form dx dz. In other words, v dot dA is the multiplication of their y components, which is x plus 2 multiplied with dx dz, such that surface integral over surface number 3 is the double integral over x and over z. So this is the integral for z going from 0 to 2 of the integral from 0 to 2 of x plus 2. So it doesn't matter which one we solve first. Let's say we solve the z integral first. Well, there is nothing z dependent in the integrand, which means that the z integral can be solved immediately and we just get a 2 at the front. And we're left with the integral from 0 to 2 of x plus 2 dx, which gives us the 2 remains. The integral of x plus 2 is x squared over 2 plus 2x, which needs to be evaluated at 0 and at 2. And this gives us twice, evaluated at 2, it gives us 2 squared over 2, so that's just 2, plus 2 times 2, which is 4, minus everything evaluated at 0 just gives us 0, so it's 2 times 6, in other words, 12. So this is the flux through surface number 3. Surface number 4, dA is in this case given by minus dx dz y hat. Therefore, v dot dA is minus x plus 2 dx dz. And notice that the expression we find now for v dot dA is the same as the expression we found for phase number 3 up to a minus sign. When we will integrate this, we integrate over x and z again from 0 to 2, both of them, meaning that our surface integral will have the same numeric value as we found for phase number 3, except for an extra minus sign. So v dot dA. We found for phase number 3 12, and that means that we will get minus 12 in this case for phase number 4. And finally, phase number 5, dA points in this case upward, and it is parallel to the xy plane, so it's of the form dx dy z hat. Therefore, v dot dA is the multiplication of their z components, so that's y times z squared minus 3 dx dy. And on this top of the cube, the value of z is a constant value of 2. We can plug in 2 for z, so within the brackets we get 2 squared minus 3, so 4 minus 3, which is just 1. And we're left with y dx dy. And this is what we need to integrate in this case for the flux over the 5th phase. So the integral over phase number 5 of v dot dA is the double integral over x going from 0 to 2 of the integral over y going from 0 to 2 of the integrand which we found to be y. Solving the x integral can be done immediately. There is no x dependence, and so we just get a 2 at the front. And we're left with the integral of y dy from 0 to 2, which is y squared divided by 2, evaluated between 0 and 2. Notice that the 2's cancel out. and evaluating y squared in 2 gives us 4, evaluating it at 0 gives us 0, so we're left with 4. So to summarize, what we find is that the surface integral over the full surface is the sum of the 5 results we found. For surface number 1 we found 16, surface number 2 was 0, number 3 was 12, number 4 was minus 12, and number 5 is 4, so we get 16 plus 0 plus 12 minus 12 plus 4, so that's 16 plus 4, in other words, 20. So this is an example of how to calculate the surface integral of a vector field. Let us now look at volume integrals. For volume integrals, we will need the volume integral both of scalar fields and of vector fields. So let us first define the volume integral for a scalar field. So we're considering some scalar field t of x, y, z, and we want to integrate it over some volume. Now, in principle, that volume can be anything, but just for me to be able to draw it, I'll draw something box-shaped. But the idea of what I'm doing can be done for any volume. There's nothing specific about this box. So here is some box. And what we want to do is to calculate the volume integral over this box of the scalar field. Now, just like we did with every other integral we've defined until now, we will subdivide the whole volume into small pieces of volume. So here is a tiny piece of the whole volume, and this small box here, I will call its volume delta tau I. And just like we did earlier, we choose some point within that box. I call that point Ci. What we will do is evaluate the function t at the point Ci, multiply it with the size of that small box, delta tau I, and then add this over the whole volume, meaning we add this for I going from 1 to n, where n is the number of small boxes we took to cover the whole big box. Now, what does this represent? Well, if we think, for instance, as the function t as it representing the mass density of the big box, what we're actually calculating is the mass, because we're calculating the mass density in every box multiplied with its volume, so we get the mass of that small box, and if we're adding them for each of the small boxes we are considering, we will get the total mass of the big box. So in this case, we will do something very similar to what we did before. We are going to take the limit of n going to infinity, and as n increases, we get something known as the volume integral, which will be denoted by t d tau. And d tau here should be thought of as an infinitesimally small volume element. If we choose to work in Cartesian coordinates, then d tau is of the form dx, dy, dz. And as we will see in one of the next lessons, if we choose to work in other coordinate systems, spherical coordinates, cylindrical coordinates, then the expression for d tau will be different, but the idea is still the same. We will take a big box, a big volume, we will subdivide it into smaller subvolumes, we evaluate the function t in each of those, and we add them up for the whole box. So this is the volume integral for a scalar field. We will see in one of the next slides how to calculate it, but we first want to introduce the volume integral also for vector fields. So if we consider a vector field v, which is a function of x, y, and z, we can represent it as its x component, which is also a function of x, y, and z, times x hat, plus similarly vy, which is a function of x, y, and z, times y hat, plus vz of x, y, and z, times z hat. And we define the volume integral of v as the volume integral of this sum, vx x hat plus vy y hat plus vz z hat d tau, where I omitted the x, y, and z dependence of each of the component functions just to make it more readable. And in this case, we can just open up the brackets. And because x hat, y hat, and z hat are actually constant vectors, they don't change as we move around in space, we can just take them out of the integral. And so we get that the volume integral of the vector field v is the sum of the volume integral of vx multiplied by x hat plus y hat multiplied by the volume integral of vy plus z hat times the volume integral of vz. Notice that each of those three integrals we are writing down here are simply volume integrals of scalar fields. So if we know how to calculate volume integrals of scalar fields, we just have to do it 3 times and we get volume integrals of vector fields. So let us now look at an example of how to calculate such a volume integral. We want to calculate the volume integral of the scalar field xyz squared over the volume of the prism drawn here. So we're looking for the integral over the prism of xyz squared d tau. Now this is a volume integral. It means it's actually a triple integral over x, y, and z, and we want to determine the boundaries of that integral. So what does it look like? Well, it's the integral where z goes from 0 to 3 dz of the integral of x going from 0 to 1 of the integral of y going from 0 to some upper bound that we will determine in a minute, dy, of the integrand, which is x, y, z squared. Now, the upper bound for y depends on the value of x we are considering, because if we look at this value of x, for instance, then the upper bound for y will be this value. While if we look at this value of x, the upper bound will only be this value. So it is actually this diagonal line here which gives us the upper bound of the y integral for each value of x, and the equation of this line is y equals 1 minus x. In other words, 1 minus x is the upper bound of the y integral. Now, because there is an x dependence in the boundary of the y integral, we need to solve the y integral first before doing the x integral. The z integral, on the other hand, is independent of the other one, so that one can be solved independently. So if we take the z squared out of the x and y integral, we are left with a product of, on the one hand, the z integral, so the integral going from 0 to 3 of z squared dz, multiplied with the double integral where x goes from 0 to 1 and y goes from 0 to 1 minus x of the integrand, which is in this case x times y. So we will calculate each of those. Now the z integral is straightforward. The integral of z squared is z cubed over 3. So this is z cubed over 3, and it needs to be evaluated at 0 and at 3. Evaluating it at 3 gives us 3 cubed over 3, so that's 3 squared, which is 9. Minus evaluating it at 0 just gives 0, so we find 9 for the z integral. We now also have the x and y integral. So the xy integral, which is, I'll rewrite it here, it's the integral of 0 to 1 dx of the integral of 0 to 1 minus x dy of xy. Notice that the x itself in the integrand can be taken out of the y integral. So this gives us the integral of 0 to 1 of x times the integral of 0 to 1 minus x of y dy dx. Now the integral of y dy is y squared over 2. So this is the integral from 0 to 1 of x times y squared over 2 evaluated between 0 and 1 minus x dx, which gives us the 1/2 can just come out of the integral, so it is 1/2 times the integral from 0 to 1 of x multiplied with y squared evaluated at 1 minus x is 1 minus x squared, minus evaluating it at 0 just gives 0 dx. So we're left with 1/2 times, if we work out the brackets, we get the integral of 0 to 1 of x minus 2x squared plus x cubed dx, which is 1/2 times the integral of x is x squared divided by 2 minus the integral of 2x squared is 2x cubed divided by 3 plus the integral of x cubed is x to the power 4 divided by 4. And we need to evaluate this between 0 and 1. Now evaluating it all at 1 just means replacing all the x's so the numerators are all 1. And plugging in 0 just gives 0 for everything. And so we're left with 1/2 times what we get if we replace all the x's by 1, which is 1/2 minus 2/3 plus 1/4, which if we put everything on the common denominator of 12 gives us 6 minus 8 plus 3. So we get 1/2 times 6 minus 8 is minus 2 plus 3 is 1, so that's 1/12, meaning that this is 1 over 24. And so the actual volume integral we are looking for, so that is xy z squared d tau, is the product of the two integrals we found. The z integral was equal to 9 and the xy integral was equal to 1 over 24, which can be simplified by dividing numerator and denominator by 3, so we get 3/8. So this is the value of the volume integral of this specific scalar field over this prism. This is how to calculate volume integrals. In the next lesson, we will look at the fundamental theorem of calculus, which relates integrals and derivatives, and we will see how it works for integrals involving gradients, divergences, and curls. I'll see you next time.